And the microphone, you want to use my microphone?
Yeah, like you can use audio channel.
Okay.
Okay, hello again, and welcome to this week's Colloquium. Today we are pleased to have Professor Oleg Smirnov from Rhodes University and SARAO, and he's going to talk to us about dynamic imaging with MeerKAT. Thank you, Oleg, for accepting our invitation, and the floor is yours.
Okay, great. Well, thanks very much for having me. This is a very fun subject to speak about. So dynamic imaging or imaging time axis. And I also like the subject because it's been very much a personal adventure for me. If you had told me in 2020, my comfort zone was always to write software and make pretty images of radio galaxies and galaxy clusters and whatnot. So if in 2020 you told me I'd be doing solar system astronomy and pulsars, I would have said, quick, go get yourself a COVID test. And like every good adventure story, it starts with a crazy idea. And I like to use this with radio astronomers because they struggle to identify this object. You folks might have an easier time. Can anyone tell me what's that on the screen there? Not a usual radio target, certainly.
The moon?
It's a moon. It's not a moon.
Callisto?
Yes, precisely. So that's Callisto. That's an object radio astronomers don't think about much, but this colleague of mine, Nick from Sweden, brought us this crazy idea. He said, can we use MeerKAT to look for OAH masers on Callisto? And the rationale for that is that Callisto is expected to have a bit of an atmosphere, and some water is predicted, has not been detected by Galileo. But with some optimistic assumptions, you can imagine a scenario where the water is dissociated and you get OH, and that gets pumped up and starts mazing. And so we had, I think it was Ruby Van Rooyen who ran some models, and she said, yeah, if you make some optimistic predictions about the models, you might have just enough of OH, mazed OH emission to be detected by MeerKAT, because MeerKAT is so sensitive. And that's a very cool idea because it's completely novel way than to probe for water on icy moons or icy bodies in the solar system. And it's not even that crazy an idea because it has actually been done on comets. So there have been single dish observations of comets where as they get closer to the sun, the same thing happens and OH emission is detected. But of course, the thing with comets is that they don't usually sit next to Jupiter. Well, there was one famous one, but it didn't last long. And of course, Jupiter is a problem because it's big and it's bright and it's always challenging to image in the presence of a big bright source. So as we were discussing the OH observations, somebody said, hey, wait a minute, we have some science verifications observations of Jupiter in the archive. And turns out there was one observation that was done during the Great Conjunction in 2020. I didn't even know this because the commissioning scientist who took this observation went on to another position 6 months later. So it was sitting there orphaned. I just, much to my surprise, I discovered it. So we said, right, well, let's at least image Jupiter first before we go for OH, just to figure out if we can image Jupiter properly. And of course, imaging Jupiter is a problem. I mean, deep imaging in radio, of course, is very different than imaging in optical. But what it shares is that, we both like to take pictures of landscapes. We don't like to photograph kids or dogs in low light because they don't sit still. This problem is even more of a problem in radio interferometry because you're imaging, you're taking data in Fourier space. So you're kind of implicitly assuming that the Fourier modes corresponding to your image stay the same over the 9 hours that it takes you to measure them and build them up. If the underlying image is changing, that means you're actually measuring different Fourier modes, and then the Fourier transform doesn't just cause a problem where the moving object is, it causes a problem all over the map. And Jupiter in this case is very much a problem child because it's massively bright and outbound. It's got its radiation belts. It's moving, it's got a 10-hour period. So, on the time scale of our observation, everything changes. Plus, of course, it's moving with respect to the background radio sources in the sky. So it was clear that we would need to, instead of making a deep image, we need to learn to make movies. So I taught myself to make movies, and that could be the subject of a whole different colloquium. I'll just give you the result here. This was the final movie of that observation. And you can follow this link if you want to see a high resolution version at your leisure. I call this movie the astronomer's bingo, because you show it to a professional astronomer and you say, hey, how many interesting things can you spot in this movie and what are they? And it takes them quite a while to work it out, especially optical astronomers not used to looking at radio maps. So I don't really have time to play the full game with you, so I'll have to give it all away. At the center, of course, is Jupiter. And here's a zoom of the center, and here's yet another zoom into Jupiter. The planet itself is this disk in the middle, right? What you're seeing is radio emission from the radiation belts surrounding Jupiter. Because we have polarization measurements, we can plot magnetic field vectors. So you can see that Jupiter is this nice, beautiful dipole, but because the magnetic axis is tilted, just like the Earth's, as it rotates, and this observation is about 9 hours. You can see timestamps in the corner there. So over the 9 hours of observation, we observe almost a complete rotation, and because of the tilted axis, the magnetic belts are booming around. That's why you see the stooping motion. That's what creates most of the imaging problems. Saturn is rather boring in comparison. It's this blob here. It doesn't have a strong magnetic field, so it's not doing that same spectacular show for us. The only way you can tell it's Saturn is because it's moving with respect to the other background sources, right? And you'd be surprised how long it takes, how long astronomers eyeball this movie before they can work that out. But then the other thing we were pleasantly surprised to see, there's a couple of very classical radio galaxies showing up. So the conjunction was a lot more interesting in radio, right? We didn't just have two pretty planets coming together. We have two supermassive black holes arriving on the scene for the bombing. Callisto, by the way, we did detect. If you look up there in that little inset, in the ellipsoid there's a little faint dot moving. And that image is actually an average of a 5-scan sliding mean, 5-frame sliding mean. So that's why the background sources are slightly smudged. And you can see Callisto showing up there as a really faint dot, which is very cool because it's like a 150 Kelvin chunk of rock, and we're detecting thermal radio emission from it. That's how sensitive MeerKAT is. Nice little, very pretty radio galaxy drifting at the top there. But anyway, as we were eyeballing and admiring this movie, there was another thing that caught our attention, and that's here in the circle. You can see this thing popping up for about 45 minutes. And that, of course, got us very excited because radio transients are rare and always very interesting. So we forgot about Callisto, we forgot about OH, and we still haven't remembered, in case you ask, still haven't got come back to that idea. So we went off chasing that transient, and oh yeah, I can show you what else we got from that observation, right? So because we have radio data, and because MeerKAT is inherently it's a spectrometer, you get a spectrum at every pixel, we can construct things we call dynamic spectra. So that's the plots you see here. This is the time axis, this is the frequency axis. These are the Stokes parameters. Stokes are at the top, and here U and V. And so now you can see the frequency structure of the event. And you can see that it was a kind of a very bright thing that came on for about 45 minutes, quite chromatic. Right? It started, and you can see it starts in low frequency and then taking off higher frequency. Super polarized, in fact, it's 100% polarized, mostly linear. The polarization shows a nice, this positive negative feature you see in Q and U. That simply means that your polarization vector is rotating around over the band, which means it's being Faraday rotated by, this is called rotation measure, this Faraday rotation in interstellar medium. And the rotation measure was consistent with something called the Obermann map, which shows the rotation measure over the plane of the galaxy. Galactic latitude of -27, so kind of high, but not outrageously high. And yeah, that was that. A very puzzling object. So we said, well, let's get some more MeerKAT time and try to chase this thing down. So we did some follow-up observations, and here's a map of one of the follow-up observations. Of course, by the time you're following up, Jupiter and Saturn are gone. So you're kind of back to the normal regime of taking a long, deep still image. And much to our satisfaction, the source was still there. So you can see here's an insert, it's this thing here. So it was still there in the map, it was still blinking away. If you made time slices, you could see that it was variable, going up by a factor of 10 or 20. And that still didn't tell us what it was. For a long time, I think we spoke with Patrick Wild. Our working theory was that it was a brown dwarf. And the project repository was actually called the Brown Dwarf Mining Project for a while. We were sure it was a dwarf, we convinced ourselves it was a dwarf, until during one of the follow-up observations, the MeerKAT people, and MeerKAT is a commensal pulsar search engine that's attached to MeerKAT. Anytime you're using MeerKAT, MeerKAT is there looking for funny transient things in the data, unless you ask them to switch it off. And during one of these follow-up observations, the MeerKAT people contacted us and said, hey, there's pulses in your, we are detecting pulses in your observation. Of course, they detect pulses, but they don't have spatial localization. They've got like a coherent beam that's super big. But they could give me the timestamps of the pulses. And then with those timestamps, I went and matched them out to the light curve of our object. And I saw that they detect pulses exactly when our object is flaring up. And then finally, the penny dropped. We realized, well, this is no dwarf. This is some kind of neutron star, obviously, if it's giving radio pulses. So we conducted a full follow-up with the pulsar timing engine enabled to really get to the bottom of this. And got some very lovely results. So here I'm showing you dynamic spectra from the pulsar timing engine. So once you've got the pulsar timing engine switched on, you can stare at the source and you can do very high time and frequency resolution. And this is what it looks like, right? So each one of these plots is about roughly an hour, maybe 45 minutes in time, the entire band and frequency. And you can see the emission is doing all this crazy stuff in time and frequency. And this is kind of, each individual hour is consistent with scintillation. Pulsars are very small objects, so they will scintillate, they will refract in the interstellar medium, give this time frequency signature. What's really unusual here is that how much that signature changes from hour to hour. This is too mysterious. We can't explain it. Normally, you would expect a scintillation signature that's more or less, well, that changes on a time scale of months or years, because that's how long it takes for the state to drift to a new line of sight. But this is something really strange. It must be either something very close to us, so structures in the solar wind that's causing the scintillation, or it must be something very close to the pulsar in its immediate environment. More dynamic spectra from the same observation, you can see from hour to hour, the pattern is really changing. So this was cool, but then we said, well, what about visibilities? What about what can we extract from imaging data? And if you run MeerKAT with the pulsar engine, you are essentially getting two independent data streams, right? You've got your high time resolution data from the pulsar engine, and that's narrowly from a beam, narrowly focused on the source. But at the same time, you're also collecting visibilities, which give you information on everything else that's in the field. And that you get at a lower resolution in time and frequency, so say typically 8 seconds in time, 4,000 channels. But that's for the entire field of view, right? So we said, okay, well, maybe what we can do is we can make a deep image of the full field with our multiple synthesis, do deconvolution to get the most complete sky model of everything that's static in the field, subtract it, look at the residual visibilities, and then once we've got that, we can make high cadence images, we can make snapshot images, and now we can construct light curves. And we can do that for every source in the field. That's the beauty of this. The pulsar timing engine, you have to point in advance, you have to know where the source is. The thing with visibility is we can do for every source in the field, and we can do it, we can go back and do it with any observation archive. And then we can also do, this is a more expensive operation, but very straightforward, rephase the visibilities to a particular source and construct dynamic spectra. They're going to be at lower resolution than from pulsar timing, but maybe they're still useful. And these are essentially these two ways. If you look at our pulsar, there are different ways of measuring the same thing. So we should hope the results are consistent, and turns out that they are. So if you look at the top there, you've got dynamic spectra constructed from the visibility data. At the bottom, you've got the pulsar timing engine dynamic spectra. And those 5 blocks, 1, 2, 3, 4, 5, correspond to 5 blocks across there. And you can kind of, if you look, you can see the same structures popping up. So you can get that information from visibilities. It's just more noisy, lower time frequency resolution. If you look at the light curves, so this is a light curve from the visibilities extracted for the original detection event. And you can see this thing got massively bright. Right? This is the original detection event, that big booming flare during the Jupiter observation. If you look at visibilities in the follow-up observations, well, you see nothing in the raw light curves. These are 8-second light curves, radio light curves. If you do a bit of smoothing in time, then you see that, you know, once you filter to a particular time scale, you start seeing peaks popping up in the light curve. And this is kind of the case for all the follow-up observations. This is an observation in MeerKAT. Again, raw light curve. Maybe just a little bit here, but you apply smoothing and the nice peaks pop up. And this was the one UHF observation where we saw the most activity from this thing. So this kind of led us down the rabbit hole of high time cadence imaging. To finish the story of the pulsar, there was a bit of a, well, first of all, we still don't have a full explanation for what it does, but we needed the name. And I was very fond, for a while, we thought it was an RATT. And RATT stands for rotating radio transient. So it's kind of like a sick pulsar that just pops up and disappears. And for a while, I thought, well, that's great, it's an RATT. And it's a very nice name because it's going to be the RATT. And then Ben Stappers told me, no, you're not allowed to call it an RATT because you're seeing it as a source on all the follow-ups. A true RATT is supposed to disappear. So that was, I was briefly annoyed because there goes my joke. But then I was so annoyed that I came up with a much better name for it, which is a parrot. And it's very accurate, right? Because it's a pulsar with anomalous refraction recurring on odd time scales. Which is true, that's exactly what's going on with it. It's also very nice because now it's the RATT parrot, and the RATT parrot, of course, is a famous or infamous, depending on how you look at it, pub in Grahamstown, right next to campus, where Justin Jonas spent a lot of time in the formative years of MeerKAT. So the RATT parrot has had a huge influence on MeerKAT, informally. So I was quite pleased that we could make a reference to that. Also, the RATT parrot was where I had a big technical breakthrough with Cyril Tass back in 2014. And that led to a nice paper, which led to calibration techniques, which led into this work. So it all fit together very nicely. So that was the story of the parrot. And after that, there was another pub that entered the picture, the Woodcutter's Arms in Hog Bay. And I don't want to give you the wrong impression. I don't actually spend all my time in pubs. I just seem to have a lot of scientific breakthroughs in them when I do go. So as we wrapped up the pilot paper, I was having a beer with Ian Haywood at the Woodcutter's Arms. And he was, at the time, he was getting into the same kind of work. He was also starting to open up the time axis. And we had a beer and we said, well, hey, this is actually, we should be doing this all the time with all the MeerKAT observations. And the more beers we had, the more feasible it seemed. So after a few pints of pale ale, we convinced each other that this was a perfectly reasonable thing to do and entirely practical. And this led to Ian kind of crystallized that subsequently at the talk he gave at the MeerKAT 5 meeting. He said we should build the robots. We need a robot that moves backward in time and trolls through the MeerKAT archive and opens up the time axis and looks for these things. And we need a robot that moves forward in time, that looks for new events commensally with observations that are going on. And of course, these are two very different problems computationally, right? Because if you're moving backwards in time, you don't care if your robot is slow and inefficient. It's a highly parallel problem. You can build an army of robots. Moving forward in time, it becomes a real-time processing problem. Very different. But anyway, we convinced ourselves it was possible, and that led to Ian's talk, and that also led us to reaching out to Breakthrough and saying, hey guys, you should be funding this. This is interesting. And they agreed, because of course Breakthrough is looking for technosignatures from extraterrestrial civilizations. Those things, by definition, these things are going to be transient events. So learning to look for physical transient events will improve your capability of searching for technosignatures. So they funded this project, and basically last year, yeah, it's only been a year. I think last year in March we finally kicked off. The eventual aim is really to mine the entire MeerKAT archive for transients that have been overlooked. The holy grail and the stretch goal is the commensal robot that can go forward in time. What we're doing currently, well, we've processed a bunch of validation fields, including the parrot. We've processed a bunch of promising fields, things like global clusters, galactic center, and things like that, things where we can expect to find transients. I'm telling my students, hey, if you're working on some data, if you've got a calibrated data set, throw the transient search pipeline at it. And we're starting targeted searches. So a student is, for example, is pulling observations from the archive that happen to have exoplanetary systems in them. There's another project to mine for brown dwarfs, etc., etc. So that's kind of what we're doing. What it looks like in practice, we've developed this pipeline called TRON, Transient Radio Observations for Newbies. And it follows the procedure I kind of briefly referenced in the previous slide. So what you do is you start with a normal calibration and imaging pipeline. You make the best possible calibration what you can. You make the best possible radio image you can. Then you start TRON. So what you do is you subtract model visibilities from your data, and then you image the residual visibilities at the roll time cadence. So for MeerKAT, this is a snapshot image every 2 seconds or every 8 seconds, depending on the roll mode. So you end up with thousands of these snapshot images. And ideally, they should be noise-like because you've subtracted your continuum model. In practice, they're anything but. I'll be showing you some images in a second. But now that you've got these thousands of images, now what you do is you form up 4D cubes. And now you smooth these cubes to various timescales because you're looking for fast transients, you're looking for slower transients, do things like compute power spectrum, more and more later on. And then we look for stuff, we look for anything interesting along the time axis, essentially at every pixel of that image cube. When we have detections, we extract light curves. We also detect this, we can also extract light curves for every source that's already in the image. That's fairly cheap to do. And you end up with tens of thousands of light curves per observation, basically for free. And we extract dynamic spectra for extracting dynamic spectra is expensive just for computational reasons. So we only do it for really interesting sources. And this is, we colloquially refer to data reduction. This problem is data non-reduction because you start with a terabyte of visibilities and you end up with terabytes of image cubes. So you can imagine this presents a computational problem, and this presents a software problem, and this presents a data format problem. So I love fits. I hope you all love fits. I've known and I've loved fits longer than I've known and loved beer, honestly. But it was time to say goodbye, right? When you make a terabyte fits cube is just an unwieldy monster that you cannot do anything with. And of course, the spectral line people have been pushing up against this problem for a long time, but they have it easy because their data access patterns are kind of benign, right? They look at specific spectral regions, so they look at specific subsets of the spectral cube, right? When you're doing transient detection, you have to work along the time axis and you have to work along the space axis. So your data access patterns are terrible, fits is impossible to work with. Just opening up the time axis blows up the compute, blows up the storage, but at least it's largely a parallel problem. So there's, you can write parallel code to do it. So we ended up writing an entirely new software stack for this problem based on a number of technologies, which again could be a subject of a whole different talk. But key to that is something called DASC, which gives you distributed chunked array processing in Python, and something called ZAR, which is a chunked data storage format. So now all our image cubes are living in ZAR format, which means they're broken up into small cubes, but on the application side, they still look like a multidimensional fits array. And then you just have to watch your algorithm's access patterns and maybe fine tune the chunking to make sure that it matches up with your access patterns. But these things become reasonable. And the runtime of this is really become reasonable, right? We can run TRON in hours of. So for an observation of several hours, we can do the transient detection. Once you've done the calibration and imaging, you can do the transient detection in a matter of several hours. So it's not really outrageous doing it. It's not even outrageous to start think of real-time processing, right? Because on a single machine, we can do it in comparable time to the observation time. So that's the software problems that we had to overcome. And there's another problem of what's buried in the noise, Once you unroll the time axis and you look inside, you actually want to roll it back and never touch it again. Because averaging hides a lot of sins. There was an old joke back in, I don't know if any of you know Jan Norden. He was a Dutch radio astronomer, now retired. He liked to smoke cigars and pontificate. And one of his pontifications was what's buried in the noise. And we had a bit of an in-joke back in 20. I think it was Brad Frank actually that came up with it. He said, well, what's buried in the noise are the bones of Jan's enemies. Turns out the joke was on us because once we unrolled the time axis and found what's buried in the noise, Jan is actually a very nice man and he cannot possibly have that many enemies. So I can show you what we found in the noise. So let's start. This is one of the parrot follow-ups, right? This is the parrot field. This is a nice deep UHF map. This is a sort of radio image that we would be very satisfied with as a result of calibration and imaging. It's nice, it's deep, it's noise limited, there are no artifacts. If you start looking at snapshots, here's an 8-second snapshot from that. This is supposed to be entirely noise, right? It isn't. What it is that thing there is one of the brighter sources in the field, and it's being diffracted and refracted by the ionosphere. So from snapshot to snapshot, it moves around and gives this kind of thing. In the deep image, all of this averages out, and you think everything is nice. In the snapshot, you see that, and I don't know if you can see, there's a little red circle. That's where the parrot is. Right. And from 8-second to 8-second, it goes to, it goes from one snapshot to the next snapshot, it does that. Right, so the challenge is to find true astrophysical, we're looking for things that pop up, astrophysical transients. And most of the things that pop up are these things. Here it gets even brighter. Here I've included the frame where you actually see that dot there, that's the parrot. That's when the parrot is flaring up. And well, this guy is flaring up as well. And of course, these being radio images, when you get artifacts are modulated by the interferometers PSF, so they throw these things outside all over the map. So it's kind of a challenging problem. It's not just let's make residual snapshot images and look for peaks in them, because these images are full of terrible stuff. Here is the parrot popping up, here is the parrot gone, right? Here it is again. So one of the key things we developed was a detection algorithm called Bryfast, which was it was a bit of an in-joke because it was based on a piece of code called Brazoro, an automasking tool, and Bray stands for Brière, which is Brittany, which is where Cyril Tass is from. But it was an unfortunate in-joke because you try typing Bryfast in a message, autocorrect will immediately correct that to breakfast. So we keep sending each other confusing messages about breakfast. But Bryfast is basically, well, it's a peak finder, but it's got a whole lot of heuristics in it to mask out all that horrible stuff that's associated with bright sources and that's causing false detections. And it's after some tuning, it started to work very well. So we got to a point where we could detect the parrot quite reliably in all the follow-up observations where we observed it, and we weren't getting any false positives. Well, I mean, it depends on your sigma threshold that you give the algorithm. But like at about 8 sigma, we would see the parrot and we would pick up nothing else. So all that horrible stuff was being ignored by the algorithm. So of course, now we could run it on real data, and the question is, are there parrots everywhere? The answer is, alas, not in every field. We have not found a transient in every field we've looked at, but we found quite a few. So I'll show you some results that we've got in this past year, or the first year of running this thing. So this was the first paper, the first letter. We were looking at global clusters. These are old 2019 observations of global clusters by MeerKAT. We looked at 3, Omega Centauri, 47 Tucana, and Terzen 5, which I'm not showing you. And you're seeing here the deep radio maps, and the circles are the Bryfast detections that we picked up. And instead, we see the light curves, the corresponding light curves. So we picked up a known millisecond pulsar in Omega Centauri. In 47 Tucana, we picked up the top 2 are known millisecond pulsars, discovered previously by dedicated pulsar searches, right? And the third object is what we propose as a millisecond pulsar candidate because it's behaving just like a millisecond pulsar, but the pulsar people haven't found it yet. And to show you more detail, this is what the dynamic spectra from these things look like. So that top one there is the normal Satori. This one here is the one from 35. And these things are there. One is a black widow and one is a redback system. They're known spider pulsars. It's basically a pulsar that's in a tight enough orbit around the companion that is eating away at the companion. So there's lots of stuff going on in the system. There's all this matter being accreted onto the pulsar. And if the geometry is right, you're going to get eclipsing behavior. And you can see this eclipsing behavior very clearly, certainly very clearly in the top one, right? The outlining stripes. That's the pulsar eclipsing. The eclipses can be irregular, I'm told. I'm not sure I understand why. Probably something to do with because it's not just the companion that's eclipsing the pulsar, it's also all the accreting material. So that geometry probably evolves. So those were the known ones we detected. These are the pulsars in 47 Tucana. Here the picture is different because 47 Tucana is known as a scintillating cluster, which means there's lots of refracting material in the line of sight to that cluster. So their pulsars are scintillating. They're being refracted by this, refracted by plasma. And what the refraction gives you is a very spectral signature, right? So you're seeing this very irregular time frequency behavior in the top two. And then the bottom one, this is the new millisecond pulsar candidate that we're proposing as a candidate. Here, well, we think that this is actually consistent with both eclipsing, you can kind of see an alternation of red, blue, and scintillation. So that was the first thing we found on these validation fields, which was very nice. Another thing we found was a complete bonus, right? I was running BriFast on the parrot follow-up fields just to see that we could detect the parrot, right? Which we did. And in one of them, we picked up another detection. And that turned out to be associated with the Gaia star, 1300 parsecs away. Here's the light curve of that detection. So you see this kind of about an hour's burst. Up top is the dynamic spectrum of the detection. And this thing seems to be an RSCVM binary. The mechanism for the flare is called electron cyclotron laser instability, right? So it's basically a mass ejection from a companion star that reaches the star in question, and then it spirals in along the magnetic field, produces these radio flares. So this was very cool, right? Because the whole point of this observation was to follow up on the parrot transient we detected. And now in the follow-up, we're detecting another bonus transient. Kind of underscores the value of looking for transients.
I'm sorry, I guess what is the radio emission mechanism for this RCS? Because you're detecting it all the time, right?
I'm not sure actually we're detecting it all the time.
Is that new stuff just noise then in the line?
Yeah, of course. Yeah. This is just noise, but you can see the error bars. Another thing that hasn't been published yet, because we're still trying to pull all the data together, but this is an example of me telling my students, well, if you're processing data, please run the transient detectorometer just to see if you pick up something. So Athanasius was reprocessing the Galaxy Plane survey, which is the Galaxy Plane legacy survey that MeerKAT did back in 2018, 2019. And his project was, well, he's working on H2 regions. So he is just trying to make the deepest possible, reprocessing the data to make the highest quality images. And he picked up a flare, and that seems to be associated with a young M-dwarf star that's only 20 parsecs away. Interestingly, it's a candidate explanatory system, which is why this kind of thing is exciting, right? Because when they're looking for radio flares from stars, I mean, it could be a binary companion that's causing it, but it could be a star-planet interaction as well. So this was very exciting to find, very frustrating as well, because this thing turned out to be playing with us a little bit. Now, these observations were done in mosaic mode. It's a fast mosaic where the telescope is going people says 2 minutes from this pointing, then 2 minutes from this pointing, 2 minutes from this pointing, we're discovering this time sequence, 2 minutes time. And this is where we picked up with transient, and we picked it up, I think, in 74, I think. And so this is the light curve detection in pointing 74. So you can see just as the flare was rising, the telescope went to the next location. And then the next location, the source is still there, of course, but it's way out in the primary beam. This is the sensitivity towards it, it's like fractions of a percent. So all we get from the next pointing is an upper limit. And from the next one, we get an upper limit. And then we come back to 77, where we get sensitivity altogether, and you can just see it settling down. And then it seems to pick up again, and again the telescope moved up. So yeah, that's why we call it the Cohen dwarf. This is the dynamic spectra, I think, probably from the start of there. So not a lot of data to go on, but we're trying to pull it together into some kind of coherent story. Another very exciting find was by Tariq, and this is probably legit to call this a second parrot. Now we know it's a pulsar, but when we first detected it, we were joking around that we may have found an alien FM station. It was a transient event, again found in old imaging data from 2019. This is the dynamic spectrum, right? And I've never seen anything this weird. Like the thing that really weirds me out about this is you have these very strong channels of emission, which kind of switch on and off almost digitally. Right? You see these horizontal stripes, right? So that means it's emitting at a specific frequency, very steadily. These stripes are horizontal, and then it's off at that frequency and it switches to another frequency. So for this one, we did a follow-up just now, 2024 actually, maybe it was in January 2025, again with the full pulsar timing engine. And this seems to be a pulsar as well. It's a very odd pulsar, so it's a millisecond pulsar, it's half a second period. Plus on top of that half a second pulsar period, which of course we don't see in the visibility data, because visibility data is 8 seconds or 2 seconds. But what we do see in the visibility data are dropouts. So on a 5-second period, this thing has like a pulsar, people call it a nulling event, but it seems too strange for a nulling event. And on top of that, it has quasi-periodic, like roughly a minute time scale, plus or minus, burst events where it pops up. And these burst events, these are the vertical bands in this dynamic spectrum that you see. That was the observational signature that we picked up with the transient event. Well, plus on top of that is this scintillation signature, right? Because I was talking about these horizontal bands. If you take a small part of this dynamic spectrum in isolation, a pulsar person will tell you, well, of course, it's scintillating, pulsars scintillate. That's why you see this banded, very chromatic structure. What they can't explain is why this scintillation signature changes like almost digitally from one mode to the next. So there's something very weird going on there. It's in some kind of very strange environment. Maybe a companion, but how to explain 5-second dropout? That would be very extreme of it. So again, more questions than answers at the moment. It certainly suggests that our technique is kind of biased toward finding weird stuff, right? Because what are the chances? The first 2 pulsars I discover are both super weird. Here's another very neat one. This is not a pulsar. This is a radio galaxy. And back when MeerKAT had its first open time call, I was involved on a project with Bernie Fanerov. Now, Bernie Fanerov wrote a couple of papers about radio galaxies. You might have heard of the first one. I was not involved with the first one because I think I was one. And then he wrote another paper on radio galaxies, which was published a couple of years ago. Nice long break, but Bernie was busy with other things. I was involved in the second one, and my job was to make deep images of these radio galaxies. And we had 4 for the paper. 3 of them came out very nicely. The 4th one was just completely annoying, right? And I took it as personal affront. No matter what I did, I ended up with something like this, these horrible radials, spiky artifacts. And, you know, I kind of built my scientific reputation on making high quality images. And here's this thing, which I couldn't massage into shape, no matter what I tried. So I beat my head against the wall for, I don't know, weeks or months. And eventually we ended up publishing in this state. We said, well, yeah, we don't know. We just can't get a good, decent image of this. We don't know. Now this year I thought, well, okay, now I have this new hammer called the transient detector. Let me go back and hammer at this problem with my new hammer. So I went back and ran to Tron and I made a light curve for the AGN core. And the light curve came out like that. I thought, okay, wait a minute, the AGN core is like highly variable. Of course I can't get a decent image because that's what's causing the problem. I also got very excited because I thought, well, AGN variability on such timescales is unprecedented. So I was excited for about half an hour until it occurred to me to eyeball the snapshot images around the time the AGN was supposedly peaking. And this is what I found in the snapshot images. So these are animations of those two flare events. So this is the AGN here. And you see that thing buzzing through? So twice this thing was photobombed by a UFO. Well, I mean, technically it was a UFO, right? Because it was definitely flying and it took me a while to identify it. So turns out ChatGPT is super useful for these situations, right? Unless you have a student you can throw the problem at. Basically, I just measured how quickly this thing was moving. I asked ChatGPT, okay, if I've got an object that's moving at this angular velocity, if it's an orbit, where is it an orbit? Turns out it's Galileo. So we just had the blind bad luck to schedule our observation when the AGN was right next to a Galileo flight path. So it ended up buzzing through twice, and especially in the second instance, you can see it's so bright it kind of saturates the image. What it's doing is it's completely screwing the calibration solutions during the time that passes through. And that translates, because the AGN is the brightest source in the field, that kind of translates onto the AGN, so that creates an apparent flare in the AGN. It's not flaring, it's the calibration amplitude is doing that. So this is kind of bad luck, but also makes me think that, I mean, this is deterministic, I don't know where the acceptance are. So we actually need better tools to tell us, you know, if we had tools back on this field of observation, we could have avoided this situation. Also, of course, it's interesting, I can tell the breakthrough people, hey, we've got a technosignature. Another lesson of this is that opening up the time axis can improve your regular imaging, right? Because now that I know this, now next thing on my list, I'm gonna flag away the time slots where this thing is buzzing through, and hopefully I can finally have a, long after the fact, I can have a decent image of the fading galaxy. And we actually saw the example of this in the galaxy plane data that Athanasius was reducing. We didn't see satellites there, but we saw time slots where some sources were getting brighter and other sources were getting dimmer. And that was briefly puzzling until we realized they're at the start of a scan. So what's happening is the antennas haven't fully settled. So you have a couple of integrations where your sensitivity is skewed over the field. So again, opening up the time axis can improve your regular observations as well, if you feed that information back in. Okay, and for the last bit, I'll tell you about where we're going with this in the future, apart from just, of course, mining the MeerKAT archive. So I said peak finding, right? Brifast is a peak finding algorithm in residual maps. Now, if you think about peak finding, well, it's obviously going to be very limited, right? So if you look at the detections we've made so far, for something like an eclipse and pulsar, peak finding is going to work very well because you have this nice regular light curve with nice well-defined peaks. But what if this thing is too faint for the peak to pop up on the bottom threshold? We're going to miss those. For scintillation, it's even worse, right? We were lucky here to pick up these things with the peak finder because this bit here and that bit there was so bright and juicy, causing a peak in the wideband light curve. But if you're making a wideband light curve, you're collapsing the frequency axis here, you're actually washing out the variability you're looking for, right? So, can we do better than peak finding? Can we look for periodicity somehow, and can we look for these kinds of patterns? So there's some encouraging results there. Now, if you look, this is a work in progress. Tariq is following up on his pulsar. If we make a power spectrum of the light curve of that weird radio station pulsar, this is a This is a vanilla radio source sitting next to it in the field. So this is now the power spectrum of the light curve, right? So this is telling you the amount of variability for each particular time scale, more or less. And you can see it's kind of flattish, right? It's what you would expect from a, pure noise. It kind of picks up towards the low order modes because that's where things like instrumental variability come in. You've got the primary beam is rotating, so that imposes a slow variation. You've got some drifts in amplitude, so you kind of see power in the low order modes. But if you look at the pulsar, you're seeing something very different, right? You're seeing that very distinct peak. That's the 5-second dropouts I was talking about. They're super periodic, so it's just one clear component that pops up. And then you see a whole little bump there, and that corresponds to the 1 minute pseudo period that we're seeing on top of that. So one idea we have is this is fairly straightforward to compute for every pixel again. If you have a cube on time, we can flip that into the Fourier domain, and now we have a power spectrum at every pixel. Now we can start looking for these kinds of things in the image beam. And this is obviously going to be more powerful than just looking for peaks. Because if you have, for example, an eclipsing pulsar that's sitting below the noise or below your detection threshold, the periodicity is still a very strong signature. So this should pop up on the power spectrum. Another thing we started to look at is called variance imaging. So what we do there is, instead of making wideband snapshots, what we do is we make snapshots across a number of subbands. So instead of just the time axis, we also have a frequency axis. How many subbands? Well, it becomes a question of disk space, as you can imagine. It's bad enough opening up the time axis, adding a frequency dimension to it as well. So we started with small numbers like 8 subbands. But for that 47 Buckner field, what I'm showing you, once we made those cubes, what we can do is we can compute statistics such as variance. Variance at every pixel as a function of time, variance and frequency. Or say the total variance of each pixel as a function of time and frequency, plus higher order modes. And so what I'm showing you here, this is the 47 Buckner observation. And this is a variance map made from that same data. So what you can see in the variance map is that all these sources completely disappear because they're flat. They only have all their variance is entirely due to thermal noise. But what pops up are the circles there. The small circles are known millisecond pulsars, known from pulsar observations. The bigger circles, 1, 2, 3, and ignore the fourth one, that's false positive. The big circles in the square are the 3 millisecond pulsars that we picked up at peak finding. Right? Now, if you look in the variance map, you see that a whole bunch of other millisecond pulsars are popping up loud and clear in this variance map. So I count at least 10, at least 7 others. So this kind of tells me that with variance imaging, we can actually pretty much double or triple our detection rate, certainly towards scintillating pulsars like the ones on 47 Tucana. Because if you look at these kinds of dynamic spectra, a variance measure is exactly the sort of thing that will pick up this behavior. And then, of course, you don't have to do just variance. You can, and then massive globe at the top there. And that massive globe is actually the brightest source in the field. And this is something radio astronomers rarely appreciate. And I should have known this about this, but I forgot. And I only rediscovered it when I made this image. We kind of think of thermal noise in our images as being constant, but of course, thermal noise doesn't just come from the receiver. Noise also comes from the source. So the brightest sources in your map will have an additional noise component due to its own, and that's what we're seeing in variance map. The brightest sources have their own increased variance, but of course, that's kind of easy to discriminate because you know what the brightest sources are. So what you want to look for is faint sources with high variance. And this, I only made this image a couple of weeks ago, so we still have to turn this into a proper detection algorithm. And of course, you don't have to stop with variance. You can compute higher order statistics such as skew and kurtosis. And you can see that in skew and kurtosis, the bright sources disappear because their variance, their extra variance is entirely Gaussian. But in the kurtosis map, all of these millisecond pulses pop up. And the fascinating one there, I think this is my last real slide. If I zoom into this, showing you all the non-millisecond pulsars, look at that one. This is what I need to see. So this is the cheap image. look at the one at the top one, the top center. That's a millisecond pulsar. You start by pulsar timing. There is no source dynamic at the image, right? It's super weak. But in the variance map, that thing pops up, and in the kurtosis map, it pops up loud and clear. So this is an example of a source that's too weak to be detected, even in normal imaging. But this kind of variance imaging really points to it. Anyway, I think that's about all I had to say. In conclusion, what can I say? Well, MeerKAT is absolutely fantastic for this, because if you want to look for transients, instantaneous sensitivity is what kind of rules the roost. And MeerKAT is truly the best instrument for this kind of work. And it's not work, but there's some effort that it can be made to work. And as I said a couple of slides ago, dynamic imaging, if you take the products of that and feed it back into your regular imaging, you can improve your regular images. And the show is ramping up, we're posting more and more data. So maybe same time next year, I will have much more exciting transients to talk about. But yeah, thank you very much. I'll take questions now.
I don't know if I understood you correctly, but you were saying that MeerKAT cannot really say where the source is. It can just detect a pulsar because it's a wide field instrument. But then you talked later about the pulsar timing with a narrow field. I'm not quite sure if it's one in the, I mean, yeah, I didn't quite understand that.
Yeah, so it's the difference between the, so schematically, if you have, so this might be your MeerKAT field of view. What MeerKAT does for the search is they form incoherent beams, which correspond to maybe regions this big. And they form a few of them. So there's one at the center. I don't remember how many there are, something like 8. And then they're searching for pulses within these incoherent beams. So anywhere in the incoherent beam would be a pulse. So your localization is this big, right? Whereas your resolution element and visibilities is this.
Right.
So that's why we could localize, because they could see a pulse in this, and the timestamps we could, because we already suspected this object, we could match the timestamps with this. Now, when you're doing the pulsar timing engine, you do coherent beams instead, where you sum up all the antenna voltages with a phase ramp to focus on a particular direction, and that's pretty much almost the same thing as an interferometer fixed. Slightly larger because then they use the inner antennas in the array, but basically that's the difference. So full field of view, incoherent beam, coherent beam.
Thanks.
Once you know where the object is, you form a coherent beam, but you have to know where it is.
Okay, yeah, thanks, that was really interesting. Two questions. One is with the Galileo satellite, affecting the image. How is there a way to detect those kind of things automatically? Because obviously that hasn't been flagged as normal RFI, but is it affecting a whole lot of our images?
Yeah,
it's not noticed.
I'm sure it is. Now that we know to look for them, we should be. Because of course, well, something like this would be, this is borderline. I think if you play with your automatic flagging, well, automatic flagging looks for peaks and visibilities. Visibilities, by definition, the signals kind of, a spatially localized signal will be spread out on the visibilities. A signal like this is bright enough that if you do very aggressive flagging, you might flag this one. A signal like this will never be flagged by visibility flagging because it's actually fainter than the AGN itself. Right? If it's not bright enough, if it's not bright enough to look brighter than an astrophysical source, it's certainly not going to be flagged. So I think the only way to catch these things is with the time lapse, right? Well, A, and B, of course, we know where Galileo satellites are, so they really should be.
The other question is in terms of the data storage, how is data being lost because there isn't storage space and people just on saving all of this time as old data, or is it's saved somewhere, but eventually we'll get to process?
Well, it's not yet. It's not lost because the visibilities in the MeerKAT archive are stored at the raw resolution. If you start doing an imaging survey, then you have. Normally, people don't think about this during imaging because terabytes of visibilities go to gigabytes of images. right? If you've got terabytes of visibility, it's going to terabytes of images. Now you have to start, if you're going to retain those imaging products, yeah, now you have to make plans. But in terms of having access to the original data, the original time access, all that information is still there in archives.
First.
I don't know if this is a stupid question or not, but on your last example, you were talking about variance mapping and how that can reveal some of those millisecond pulsars. But on that, the next slide, sorry, the second to last slide, that one, you say that there in that detection there is nothing in that top sort of well, that circle over there.
Yeah.
And then in the variance map it shows up. How do we know that that's not the variance from the top source leaking into the bottom?
No, that's not. Yeah, that's an excellent question. I've been pondering the same. I think it's not because in the way it's such a nice compact. There is leakage because yeah, of course, and source detected interferometrically will have PSF side lobes, so it's not just going to be spectral variance here. It's also going to be variance in all the side lobes. This is such a nice compact peak at exactly the position, the known position of the millisecond pulsar, that I think this is definitely real. But like this stuff here, that's most probably side lobes.
Okay, yeah.
Would there be a way to like maybe adapt the drawing to like maybe faster burst service? Like given that like you found a lot of pulsars and instant fields, maybe like if you've been right.
Well, we're very much hoping to catch an FRB with this, because of course the first time scale we look at is the roll time scale of 2 to 8 seconds. But unfortunately, you would only be able to catch the brightest FRBs, right? Because an FRB is so short duration that even in 2-second data, it's already sufficiently washed out. But if you look at the numbers, the brightest ones should be popping up. So I'm hoping.
Okay, I think that's the last question.
In the parrot, you showed the dynamical power spectrum, and it looked to me like it was not strictly periodic, it was more quasi-periodic. Is that correct? Or in fact, what is the period of the parrot?
Oh, the parrot is 1.6 seconds.
1.6.
Yeah, so we don't see that in, you mean the pulse of time?
Well, in the...
These dynamic spectrum.
Yeah.
Yeah, so the period you don't see at all, because the bit here, the time bit here is larger than the period.
Oh, okay, so that's not the...
What they're doing here is they are, once they've got the period, they actually fold on multiple periods to improve the signal to noise. So what you're seeing here is the combined flux from several pulses as a part of the frequency. So all this is the refraction and the scintillation that's going on in the medium.
Okay.
Okay, I think we run out of time, so thank you so much. And yeah, see you in the next video. Thank you.